In the last video, we derived this really important result, which was that if you take an enclosed space around a charge, the total electric flux through the surface is equal to the charge enclosed divided by epsilon 0. Now that's really interesting because what we derived it for was for a positive charge enclosed by a sphere. But in fact, this result holds for any situation. So we could start with a positive charge and we could enclose it by some weird shaped object. If we went around and we calculated the electric flux at every location and added it all up, we would still find that the total electric flux is the enclosed charge divided by epsilon 0. So that's really nice. It's actually really powerful. But it's only powerful for a specific set of geometries. And so we're going to talk a little bit about those geometries or those symmetries. So the three main types that we're going to deal with in this class, and the three main types for which this works pretty well, are what we would refer to as the spherical geometry, which is the one that we have here, a cylindrical geometry, or a cylindrically symmetric situation, or basically a planar geometry. Okay, so we'll go through each one of those really quickly. So the idea behind this is if I have some sort of charge, let's say a point charge, because that'll be the common case, and I enclose that with a sphere, then what I have is a situation where the electric field points radially outward everywhere, and the dA vectors point radially outward everywhere. So in this case, it looks kind of like that. And so this allows me to calculate the total electric flux rather straightforwardly, like you saw in the last video. But it also gives me a very clear answer to how much is the total flux. It's whatever this charge is divided by epsilon 0, right? In a cylindrical case, if you have, for example, a long line of charge, so here's a long tube of charge, and you encapsulate it with this sort of imaginary cylinder, in this case, the electric field points outward everywhere, and it kind of slides along the top here, as we'll see in one of the next videos. So there's no flux through the top or the bottom, and all the flux are given by this space sort of surrounding the cylinder. And what that lets us do is deal with sort of this as being the charge enclosed, whatever amount of charge is living inside that cylinder, and it allows us to calculate the electric field, as you'll see in a moment. Now the last geometry is what we'd call a planar geometry. So this is a flat plane of charge. So there's some amount of charge that's sort of sitting all over this surface, and it's sort of uniformly distributed across the surface. And the way that we would go about dealing with that is drawing a little, what we would call a pillbox that sort of intersects with the surface, like this, above and below. So I'll just draw it a little bit longer. So kind of, if you think about sort of a box that is situated sort of in the middle of this planar geometry, and it's these flat sides, this side and this side are flat with respect to the planar geometry itself, then in this case, this charge distribution produces an electric field that points perpendicular to these flat sides, but it slides along the sides of that box. And so all the flux is, in this case, from the top and the bottom, and there's no flux out the sides, right? So these three specific geometries, the spherical case, the cylindrical case, and this planar case, are where this enclosed charge idea and the idea of Gauss's law are going to be applied. There's more complicated geometries where this kind of works, but we're not going to deal with them in this class. We will focus on mostly the spherical, the cylindrical, and sometimes the planar case.